Hi, my name is David Ho, and I work for the Hydrologic Engineering Center in Davis, California. This video series is part of the basic HEC-HMS class. In this video, we will be providing an introduction to the surface runoff transform capabilities in the HMS software. The objectives for this lecture will be to go over where the surface runoff process fits in to the rainfall runoff modeling process, and to review the transform methods available in HMS. We start our discussion by reviewing the physical processes that take place once you start getting precipitation onto your watershed. So this figure shows the various hydrologic processes that can occur once rainfall falls on the ground. So much of the rainfall is subject to different losses. You can get infiltration of your rainfall into the soil. There could be rainfall that falls on canopy and gets stuck there. And your ground surface may contain storage that traps rainfall or movement of flow. So these losses can be subtracted from the amount of precipitation that falls on the basin. When losses are subtracted, we are left with the excess precipitation, meaning it's the rainfall amount left over after you account for the losses we just described. So excess precipitation over the basin ends up on the surface, which is then converted to a runoff and makes its way to the channel and basin outlet. In rainfall runoff modeling, we attempt to simulate the various hydrologic processes that occur when you get rainfall over a basin. The component that handles surface runoff is the transformation of excess precipitation, as shown here in red. The excess precipitation gets converted or transformed into surface runoff, which feeds into the total hydrograph. The excess precipitation just looks at the surface runoff. There are other components to the total outlet flow, such as interflow and groundwater flow, but we'll be focusing our discussion on just the transformation of excess rainfall. One of the main purposes of a rainfall runoff model is to produce a hydrograph at a specified location. A hydrograph is simply a plot of discharge versus time for a given location. The term hydrograph is often synonymous with the term discharge, and you might hear these interchangeably. The excess rainfall transformed to runoff makes up a part of the total hydrograph, which we call direct runoff. Interflow and baseflow, which deals with the subsurface movement of water, are also important components to the total hydrograph. Other descriptors to the hydrograph are the rising limb, which is the start of direct runoff up to the hydrograph peak, and the falling limb, which begins from the hydrograph peak to the end of direct runoff. Falling limb is also known as the recession limb. And then the inflection point is generally the point at which direct runoff ends and interflow or baseflow drives the rest of the hydrograph. So how do we go about transforming excess rainfall to surface runoff? In HMS, we have three transform methods available to us: the unihydrograph method, kinematic wave, and the 2D diffusion wave transform. The first method, and most well known, is the unihydrograph. So this concept was developed by a guy named Sherman. So Sherman defined the unihydrograph as the basin outflow resulting from 1 inch or 1 millimeter of direct runoff generated uniformly over the drainage area at a uniform rainfall rate during a specified period of rainfall duration. So unihydrograph is often used for lumped parameter modeling, meaning the parameters that characterize the unihydrograph is an average over the watershed area and ignores spatial variation. There are exceptions to this with the Maud-Clark method, but that we will discuss that in a different video. There are different ways to apply the unihydrograph concept. In HMS, you have the ability to select from a number of different methods, such as Clark and SCS unihydrograph methods. The second transform method available is the kinematic wave transform. The kinematic wave represents the watershed as two plane surfaces over which water runs until it reaches the channel. The water then flows down the channel to the outlet. The watershed and its channels are conceptualized as shown in this figure, where you have water move as overland flow on the plains and then as channel flow. Another way of looking at this is resembling something like an open book, where the water runs parallel to the text on the page and then into the channel that follows the book's center binding. So this method solves the energy and continuity equations for both the plains and the open channel to compute the watershed runoff. One application for using kinematic wave in HMS has been for urbanized regions, where you have gutters, ditches, or some other stormwater collector. A relatively recent feature in HMS is the ability to route water using the 2D diffusion wave method. The 2D diffusion wave transform method routes excess precipitation using the combination of the continuity and momentum equations. One of the main advantages to using this method compared to the unit hydrograph is this transform can be used to simulate the nonlinear movement of water through a subbasin. This method represents subbasins using a 2D mesh, which at this time requires HEC-RAS 2D to create. Since the transform method does occur on a grid cell by grid cell basis, as well as the routing of flow, this method allows for distributed parameter modeling, meaning the model accounts for behavior variations from a grid cell to grid cell throughout the system. The 2D diffusion wave also has the capability of spatially and temporally visualizing computed variables, such as the water surface elevation and average velocity. Thank you for listening to the Surface Runoff video series. Visit our websites to learn more about how to use HMS and follow future updates. See you in the next video on how to derive a unit hydrograph from a recorded stream flow.